Welcome to Study Loop.
In this problem, we're going to talk about projectiles. So consider that we have an object that is launched at an angle theta above the horizontal. So this angle here I'm going to call theta. And it makes a parabolic trajectory, okay, and ends up, let's say, at this point here. So what we need to consider is that all throughout the projectile's trajectory, the only force that acts on the projectile is the gravitational force pointing downwards. So this means that in the y direction, considering that the y direction points upwards and the x to the right, in the y direction, the movement will be that of a uniformly accelerated object. So delta y is v0y, the initial velocity in the y direction, times t minus 1/2 of g t squared. Okay, and in the x direction, the movement will be just the movement of a uniform motion. So it's equal to v0x times t. Now notice that if v0 is the initial velocity, the initial speed, I'm sorry, then the initial velocity in the x direction is v0 times cosine of alpha, while the initial velocity in the y direction is v0 times sine of alpha. So in the end, we can write these equations as delta y is equal to v0 sine alpha t minus 1/2 of gt squared, and delta x is v0 cosine alpha t. And in our problem, what we have is a boy who's running down an incline that makes an angle of 12 degrees with the horizontal, and then he jumps. So his trajectory will be something like this. Okay, actually, let me draw it a little smaller. His trajectory will be something like this. The initial angle he makes with the horizontal is 15 degrees. And our goal is to find, uh, given that he falls back on the inclined plane after a distance of 1.4 meters, our goal is to find what was his initial speed v0. Okay, so what I'm going to do first is to calculate how far he went in the x and y directions. So notice that we can draw here a rectangle triangle where this angle here is 12 degrees. So delta x is 1.4 meters times the cosine of 12, and this is equal to 1.37 meters. Delta y is 1.4 meters, actually minus 1.4 meters since the y direction is pointing upwards in my convention, times sine of 12, and this is equal to minus 0.29 meters. Okay, and then I'm going to take our equations. So for the x direction, we have that delta x is v0 times cosine of 15 t. I'm going to isolate t in this equation. So t is equal to delta x divided by v0 cosine of 15. And I'm going to insert this equation for the time here into the equation for the y direction. So delta y is v0 sine of theta, sine of 15 actually, times t minus 1/2 of gt squared. So it's equal to v0 sine theta delta x divided by v0 cosine 15 minus 1/2 of g delta x squared divided by v0 squared cosine squared of 15. And my goal here is to isolate v0, that's what we want to find, Uh, but first I'm going to simplify things. So delta x is tangent of 15 degrees delta x minus 1/2 of g delta x squared over v0 squared cosine squared of 15 degrees. Uh, Let me try to start isolating v0. So we have this term, and then this is equal to delta y minus tangent, actually, I'm sorry, tangent of 15 degrees delta x minus delta y. Then I'm going to multiply both sides by v0 squared and divide both sides by tangent of 15 delta x minus delta y. So v0 squared is equal to 1/2 of g delta x squared divided by cosine squared of 15 degrees times tangent of 15 delta x minus delta y. So v0 is delta x divided by cosine of 15 times the square root of g over 2 times the tangent of 15 delta x minus delta y. Now we can substitute the numbers. So v0 is delta x. Remember that it's equal to 1.37 meters. And we divide it by cosine of 15 times the square root of 9.8 meters per second squared divided by 2 times the tangent of 15 times delta x. That's 1.37 meters minus delta y, and delta y is minus 0.29, so in the end it's plus 0.29 meters. So v0 is equal to 3.87. I'm sorry, this is not true. V0 is equal to 3.87, I'm sorry for that, meters per second. Which concludes our exercise.